Welcome to my presentation on heat transfer. This is my first activity and this presentation has been titled as Analysis of Heat Transfer by Annealing. The contents of this presentation involves the annealing process, the objective of the problem statement itself, a schematic representation of the problem, certain assumptions have been made while solving the problem, analysis, and a couple of comments have been put as well. Coming to the process of annealing. Here in this picture, we can see a bar that is undergoing the annealing process. Now what is this process? It is a heat treatment process that changes the physical and the chemical properties of a material. It increases the ductility, reduces the hardness to make the material more workable. Now the objective of the problem. We have to find the upper surface temperature of a silicon wafer. The silicon wafer has been used in the problem and it is mentioned that if the silicon wafer, if the surface temperatures or the difference in the temperatures of the upper surface and the lower surface of the silicon wafer is less than 2 degrees Celsius, then the silicon wafer will be able to avoid warping and some other damages as well. Thus, the temperature of the upper surface of the wafer is need to be known. The problem statement. Let me put it in short. We can see a silicon wafer that has a thickness of 0.78 mm. The lower surface temperature of the silicon wafer is given as 997 degrees Celsius. The silicon wafer has been put inside an evacuated chamber. The wall temperature of the chamber is 27 degrees Celsius. There are heating lamps that provide a radiant flux of 3 × 10⁵ watt per meter square. An emissivity that equals its absorptivity is used, that is, epsilon is equal to alpha is equals to 0.65. The value of the radiant flux has been given and the thermal conductivity of the silicon wafer has been given as 30 watt per meter Kelvin. The representation of the given problem. The control volume has been shown in dashed lines and all the given criterias are mentioned in this picture. On the right hand side we can see the easier representation that shows the heat transfer that is going on. We can see the alpha LQ double dash S. It is the amount of radiation that is being absorbed by the silicon wafer. Some amount is being radiated out as well, that is mentioned as Q double dash rad. The Q double dash CD shows the conduction process as the conduction is going on from the upper surface to the lower surface of the silicon wafer. We have to find the temperature of the upper surface. Some assumptions has been made. Steady state conditions which say that the temperature will not change over time. One-dimensional conduction inside the wafer. This is because the heat is being transferred only in one direction. Thus, in Fourier's heat conduction formula, we can use instead of dt dx, we can use delta t by delta x as it is a one-dimensional conduction. The radiation exchange between the surroundings and the wafer surface is between a large enclosure and a very small object, and conduction has been neglected as the wafer has been put inside an evacuated chamber. The analysis. As we have seen, there are only 3 processes going on in this problem. Some of the radiation that is being absorbed, the radiation from the heating lamps. There is radiation heat exchange with the chamber and conduction inside the wafer. Using the surface energy balance, we can put the formula in this way: E double dash in minus E double dash out equals to 0. Now The alpha Q double dash S is the amount of irradiation that is being absorbed by the silicon wafer. The Q double dash radiation involves the radiation exchange with the walls, and the Q double dash CD is the heat transfer by conduction. Now the heat transfer by radiation is seen as epsilon into sigma into T Wu to the power 4 minus T SUR to the power 4. Here TWU is the upper surface temperature of the wafer and the TSUR is the surrounding temperature, as the radiation is being conducted by the upper surface of the wafer as well as the surroundings, which involves the chamber walls. For conduction, we have used Fourier's heat formula, that is K delta T by L. L represents the thickness of this silicon wafer. Thus, on calculating, we get the upper surface temperature as 1273 Kelvin, which is equal to 1000 degrees Celsius. We have seen that the temperature difference between the upper surface and the lower surface is more than 2 degrees Celsius. Hence, warping of the wafer and inducing slip planes in the crystal structure will occur. The most important part of this problem solving is that we should not forget to express the radiation heat transfer in the temperature during the radiation heat transfer in Kelvin units. This was all about the problem. Thank you.